We're always hearing about the next big thing in sunscreen, right? It can be hard to keep up.
Yeah, it really can. I mean, you want to protect your skin, but then there are also all these questions about what's actually in these products,
Uh-huh.
what's safe, what's sustainable.
Exactly. So this deep dive is going to be all about one of those new things that caught my eye. Well, actually, you sent me this article.
Oh, yeah, that one.
Yeah, about this new type of sunscreen ingredient. It's actually a combination of something we've heard a lot about, zinc oxide, but then they combine it with, well, honestly, it sounds a little weird. It's called Chitosan.
Yeah, it's got kind of a sci-fi name, doesn't it? Chitosan.
It does, but that's what we're going to dig into today. What is it? What's so special about it? And what does the science say about how well it actually works? The study is all about whether this new combo, this ZNO Chitosan thing.
They call it ZNO at sea.
ZNO at sea. Okay, much better. Anyway, is it really better, safer, more eco-friendly, all that good stuff?
Oh, you're right.
So maybe we should start with the basics, right? Zinc oxide, we kind of know that one, but what about chitosan? What even is that?
So chitosan, it's actually a natural polymer. They call it a polysaccharide in the paper. Basically, it's a long chain of sugar molecules all linked together.
Huh. So it's not some lab-created chemical. That's interesting.
Nope. It comes from chitin, and you actually find chitin in a lot of places in nature. Like, it's a main component in the shells of crustaceans, shrimp, crabs, lobsters,
Oh, wow. Okay.
and also in the cell walls of fungi, like mushrooms. So they often get chitosan from those kinds of natural sources.
So they're basically recycling in a way.
Kind of, yeah. And the cool thing about chitosan is that it has a bunch of interesting properties that make it attractive for cosmetics and even things like biomedical applications.
Okay, but what kind of properties?
Well, first of all, it's biocompatible, which means it generally plays well with our bodies.
Good to know.
And it's biodegradable, meaning it breaks down naturally in the environment. So from a sustainability perspective, those are both big pluses. But there's more. Chitosan also has antioxidant activity.
Antioxidant, like what you find in blueberries and green tea.
Exactly. Antioxidants help protect against damage from things called free radicals, which can be produced by things like UV exposure.
Free radicals, yeah.
And they can damage your cells. Chitosan also has some antibacterial properties.
So it's like a multitasker.
It is. And all of these properties together is why it's been used in cosmetics for a while now. It can help moisturize the skin, protect it, and even has some wound healing potential.
Okay, that makes a lot of sense. So moisturizing and protecting the skin, that already sounds like a good foundation for something you'd want in sunscreen. But in this study, they also talk about chitosan acting as a booster, which sounds pretty cool. But what does that actually mean in the context of sunscreen?
Right, so a booster in sunscreen is essentially an ingredient that helps the main UV blocking ingredients work even better, or it adds extra benefits. Now, in the case of chitosan, there are a couple of ways it could potentially boost a sunscreen. First, it might actually enhance the UV filtering ability of zinc oxide itself.
Oh, interesting.
And second, because it's an antioxidant, it could help neutralize some of those harmful free radicals I mentioned earlier, free radicals that get generated when our skin is exposed to UV radiation. So it's like a double whammy. You get better UV blocking, and then you also have this extra layer of protection against some of the damage that UV can cause.
That's pretty awesome. So, it's not just about blocking the sun, but also about dealing with the aftermath, the damage control in a way. Okay, so we've talked about chitosan, but let's step back for a sec and talk about the broader picture here. There's this big push towards mineral sunscreens these days. We're all trying to be more mindful of what we're putting on our skin and also what ends up in the environment. Why are mineral filters like zinc oxide considered a better option, especially compared to some of the traditional chemical filters out there?
Yeah, that's a great point. I think there are a couple of key reasons why mineral sunscreens are gaining popularity. First off, there's growing concern about the potential environmental impact of some of those traditional chemical UV filters.
Right, like the stuff about coral reefs.
Exactly. There have been studies suggesting that certain chemical filters might be contributing to coral bleaching and other damage to marine ecosystems. Now, the science on this is still evolving, and there's ongoing debate about the extent of the impact, but it's definitely raised awareness and concern.
Yeah, people are definitely paying more attention.
Right. And that's where mineral filters, like zinc oxide and titanium dioxide, come in. They are generally considered to be safer for the environment. They're naturally occurring minerals, and they tend to be less likely to cause those kinds of ecological issues.
So gentler on the planet.
Right, that's the idea. And from a human health perspective, mineral filters are also generally well tolerated by the skin. They're considered to be less likely to cause irritation or allergic reactions, which is a big plus for people with sensitive skin.
So, all good things. So, I guess that brings us to the question of why even bother combining zinc oxide with Chitosan in the first place? If zinc oxide is already a good option, what are the scientists trying to achieve with this new ZNO Chitosan thing?
So think of it this way. Zinc oxide, it does its job. It blocks UV rays, but it's not perfect. The scientists in this study are basically trying to tweak it to make it even better by taking advantage of the unique properties of Chitosan.
Enhance it.
Right. And they got a couple of specific goals in mind. First, they wanted to improve the stability of zinc oxide, how well it stays dispersed and doesn't clump up.
Yeah, that makes
Because
sense.
if it clumps together, it's not going to be as effective at blocking the sun's rays.
Right, it's like if your shield is all bunched up, there are gaps for the arrows to get through.
Exactly. And then their second goal was to reduce something called the photocatalytic activity of zinc oxide.
Photo what now?
Yeah, it's a mouthful.
Definitely.
But basically, photocatalytic activity means that when zinc oxide is exposed to UV light, it can kind of go into overdrive and produce certain molecules called reactive oxygen species, or ROS. Now, sometimes ROS can be helpful, but in other cases, like on our skin, they can actually cause damage to cells and contribute to things like premature aging.
Oh, so it's like a double-edged sword. It blocks the sun, but it also has this potential side effect of generating these troublemakers.
Exactly. And those troublemakers can actually worsen some of the very problems we're trying to protect our skin from in the first place. So the researchers were hoping that by coating the zinc oxide with chitosan, they could kind of tame it a bit, reduce that photocatalytic activity, and make it safer for our skin.
Okay, I'm following you. So less collateral damage, so to speak. But how did they actually create the ZNO at CA? Like, how do you get those two things to stick together?
Well, they used a technique called ionotropic gelation, which sounds complicated, but it's actually pretty clever.
Okay.
They basically start with a solution of chitosan, those long sugar chains. Then they add in the zinc oxide nanoparticles, and they let those kind of mingle for a bit. And then they add in this other ingredient called pentasodium triphosphate, or TPP for short.
Okay, so what does the TPP do?
So TPP, you can think of it as a crosslinker. It helps to connect those long chitosan chains together, forming a sort of gel-like network. And as this network forms, it traps the zinc oxide nanoparticles within it. So it's like building a microscopic cage of chitosan around each tiny particle of zinc oxide.
Oh, cool. So it's like each little zinc oxide particle gets its own little Chitosan cocoon.
Exactly. And that's what creates the ZNO at C adduct.
Got it. So how do they know this actually worked? How did they confirm that the zinc oxide and the Chitosan were really bonded together and not just hanging out next to each other?
So to check that, they used a technique called FTIR spectroscopy, which stands for Fourier Transform Infrared Spectroscopy.
FTIR.
Yeah, it sounds intimidating, but it's basically a way of identifying molecules by looking at how they absorb infrared light. Every molecule has a unique infrared fingerprint based on how its atoms vibrate. So by comparing the FTIR spectra of pure Chitosan, a simple mix of zinc oxide and Chitosan, and their new ZNO at CIRG, they could see whether there were any new signals or shifts in the signals indicating new chemical bonds had formed.
Oh, so it's like looking for the telltale signs, the evidence that something new has been created.
Exactly. And they did find evidence. They saw some specific changes in the spectra, especially around signals related to carbon-oxygen and carbon-nitrogen bonds, which suggested that those were involved in the interaction between the zinc oxide and the chitosan.
Okay, so they had the fingerprint evidence. Now, what about how stable this new ZNO at COT is? Like, does it fall apart easily?
Yeah, that's a super important question, right? You want something that's going to hold up in a sunscreen product.
Right.
So they did a bunch of tests to look at its stability. First, they used a technique called TGA, which stands for thermogravimetric analysis.
TGA.
Right. And basically, TGA measures how much weight a sample loses as you heat it up. So different components of a material will break down and evaporate at different temperatures, and you can see that as weight loss on a graph. So they did TGA on the ZNO at CHE and found that a large percentage of the material decomposed at a certain high temperature. And based on that, they were able to calculate that the chitosan content in the ZNO at CH was really high, over 40%, which is good.
Oh, wow. So that means it's pretty tightly bound, right? It can take some heat.
Yeah, it suggests that a significant amount of chitosan was indeed successfully attached to the zinc oxide. They also used another technique called DSC, which stands for differential scanning calorimetry.
DSC, okay.
And that one looks at the energy changes that happen within a material as you heat it up.
Right.
So DSC provided more detailed information about the thermal properties of the ZNO at Kelsey.
Okay, so they grilled it and it held up pretty well. But what about its stability in a more realistic setting? Like, our skin has different pH levels, right? So would this ZNO at CH stay intact on our skin?
That's a very important point. Our skin's not just a hot plate, right?
Definitely not.
So they also looked at the stability of ZNO at C in different pH conditions, which is crucial for a topical product like sunscreen. To do this, they measured something called Zia potential. Have you heard of Zeta potential before?
I have, but honestly, I'm a bit fuzzy on the details.
So Zia potential. Well, imagine each particle of ZNO at C in a liquid has a sort of electrical charge on its surface.
Oh.
And this charge can either attract or repel other particles. Now, zeta potential is basically a measure of this charge. And it's important because if the particles have a high zeta potential, meaning they're either strongly positive or strongly negative, they're more likely to repel each other and stay dispersed in the liquid. But if the zeta potential is low, the particles might clump together, which isn't good if you want your sunscreen to spread evenly and stay effective.
Oh, okay. So like magnets, basically. Same poles repel.
Exactly. So they measured the zeta potential of both plain zinc oxide and ZNO at CH at different pH levels, from acidic to alkaline, to see how stable they were. And what they found was that the ZNO at CH had a higher zeta potential across all the pH levels tested compared to the plain zinc oxide.
Oh, so that's a good sign, right?
Yes. It means that the Chitosan coating was helping to keep the particles stable and prevent them from clumping together. In fact, they found that in very acidic conditions, the plain zinc oxide started to dissolve, which is not good for UV protection. But the Chitosan coating on the ZNO at CH helped to prevent that from happening. They also measured the particle size in different pHs, and the ZNO at C maintained a more consistent particle size, which is also a good indicator of stability.
Okay, I'm seeing a pattern here. The Chitosan is like a super protector. But hold on, didn't the study also mention that the particle size actually increased at a neutral pH, which is around the pH of our skin? And there was something about a higher sedimentation rate, too. What was that all about?
You got a good eye for detail.
Yeah.
Yeah, they did find that the average particle size of the ZNO and CH increased a bit at a pH of 7, which, as you said, is close to the pH of our skin. They think this might be because at that pH, the particles become less charged and have a tendency to stick together a bit more.
Okay, so a little bit of clumping.
A little bit. And they also noticed that the ZNO at CHH settled out of the liquid faster than plain zinc oxide. This could be due to the larger particle size, or maybe the Chitosan coating causes the formation of slightly larger, heavier structures that sink more readily. And that's something that would definitely need to be addressed when actually formulating a sunscreen, right? You want to make sure it stays nicely dispersed.
Right, so it doesn't all sink to the bottom of the bottle. But it sounds like overall, the stability is still pretty good across different pH levels, thanks to the Chitosan.
Yeah, I think that's a fair assessment.
Okay, cool. Now, what about actually seeing this new structure? Did they get any pictures? You know, is there visual confirmation that the Chitosan is actually forming this cage around the zinc oxide?
They did. They used some pretty high-tech microscopes to get a close-up look at the ZNO at CO. They used both SM, which stands for scanning electron microscopy,
SM, yeah.
and TEM, which is transmission electron microscopy.
Okay.
And those images pretty clearly showed the zinc oxide nanoparticles embedded within this matrix of Chitosan. It really did look like the Chitosan was forming a sort of web or a coating around the zinc oxide.
Cool.
They also use a technique called SEM-ED, which stands for Scanning Electron Microscopy Energy Dispersive X-ray Spectroscopy.
SEM-ED.
Yeah, it's a mouthful, but essentially it lets you identify what elements are present in a sample. And they use this to confirm that both zinc and oxygen from the zinc oxide and nitrogen and carbon from the Chitosan were present in the same particles.
So picture proof that they were indeed combined. Awesome.
Yep.
Now, let's circle back to one of the main goals they had for this new ZNO at SE, which was reducing that photocatalytic activity of the zinc oxide. Did they actually find that the Chitosan coating made a difference there?
They did,
Yeah.
and it's actually one of the most striking findings of the study. They use a test with a blue dye called acid blue 9. So basically, when this dye is exposed to UV light in the presence of something that's photocatalytically active, like plain zinc oxide, it gets broken down, and the blue color fades. So they had a solution of the dye in either plain zinc oxide or ZNO at CF and exposed them to UV light for a certain amount of time. And then they measured how much of the dye was degraded.
Okay.
And the difference was huge. The ZNO at CF showed a dramatically reduced ability to break down the dye compared to the plain zinc oxide. Like after the UV exposure, over 50% of the dye had degraded in the presence of plain zinc oxide.
Wow.
But with the ZNO at CA, less than 1% of the dye was degraded.
That's incredible. So basically, the chitosan was acting like a shield, preventing the zinc oxide from going haywire and creating all those reactive oxygen species.
Exactly. It really seemed to be effectively blocking that photocatalytic activity. So from a safety perspective, that's a big win.
Right, because those reactive oxygen species, the ROS, they're the bad guys that can damage our skin cells and contribute to aging.
Exactly.
Okay, so the chitosan gets a gold star for that. What about the direct effects on our skin cells? Did they test whether this new ZNO at CH was less toxic than regular zinc oxide?
Yes, they did. They used a test called a neutral red assay, which is a common way to assess the toxicity of substances to cells.
Okay.
And they tested this on a type of mouse skin cell. Essentially, they exposed the cells to different concentrations of either plain zinc oxide or ZNO at C, and then measured how healthy the cells were afterward.
So how did they stack up?
Well, the ZNO at C was significantly less toxic to the cells compared to the plain zinc oxide.
Yeah.
This was especially true at higher concentrations.
Yeah, that's great.
Yeah.
So safer for our cells. But why? What's the reason for this lower toxicity?
They think it might be a couple things. One possibility is that the chitosan coating acts as a barrier, reducing the amount of zinc ions that can leach out of the zinc oxide particles. Zinc ions themselves can be toxic to cells, especially in high concentrations.
Okay.
Another possibility is that the slightly larger size of the ZNO is CH particles. Remember, we talked about that.
Yeah.
That might mean they're not taken up as easily by the cells.
Right. They can't sneak in as easily.
Exactly. So there's less internal exposure to the zinc oxide.
Okay, so the chitosan is kind of like a bouncer at the door, keeping the trouble out.
Exactly.
Nice. All right. I think we've covered all the groundwork here, but now for the million-dollar question. Does this actually translate to better sun protection? Does this ZNO at CAH combo really block UV rays more effectively than plain zinc oxide?
That's the ultimate test,
Okay.
right? And the answer seems to be yes.
Yeah.
They actually formulated simple sunscreen emulsions using either plain zinc oxide or the ZNO at C, and then they measured the SPF and UVA-PF.
Okay. And just as a quick reminder for the listeners, SPF, that's the sun protection factor, tells you how well a sunscreen protects against UVB rays, the ones that cause sunburn.
Right.
And UVA-PF, that's the UVA protection factor, which indicates protection against UVA rays, the ones that penetrate deeper into the skin and contribute to aging and skin cancer.
Exactly. And what they found is that the sunscreen with ZNO at CH had both a higher SPF and a higher UVA-PF compared to the sunscreen with just plain zinc oxide.
Excellent.
Yeah, the differences were statistically significant, which means it wasn't just random chance. The chitosan really did seem to be boosting the sun protection ability of the zinc oxide.
I'm looking at the numbers in the study, and while they might not seem super high compared to some of the sunscreens you'd buy at the store, what's important is that there's a clear improvement with the ZNO at Siege.
Right. And that improvement could potentially allow you to use a lower concentration of zinc oxide overall and still achieve good protection.
And that's a big deal, right? Because using less of an ingredient can have all sorts of benefits.
Absolutely. It could mean lower manufacturing costs, which could translate to a lower price for consumers. And from an environmental perspective, it could mean less mining of zinc oxide, which can have negative environmental impacts. So it's a win-win situation.
Okay, speaking of environmental impact, we touched on this earlier, but the study does mention some concerns about zinc oxide nanoparticles in the environment, especially in water. Can you remind us what those concerns are, and how might coating them with chitosan help?
Right, so there's been growing concern in recent years about the potential harm that uncoated zinc oxide nanoparticles can cause in aquatic environments. When these nanoparticles end up in water, they can release zinc ions, and those ions can be toxic to marine life, like fish, coral reefs, algae, all sorts of organisms.
Yeah, coral reefs especially are already under so much stress.
Exactly. And in addition to releasing zinc ions, the photocatalytic activity of zinc oxide we talked about earlier, well, that can also be a problem in water. It can lead to the production of reactive oxygen species in the water, and those can also be harmful to aquatic life. So the idea behind coating the zinc oxide with chitosan is that it could help reduce both the release of zinc ions and that photocatalytic activity, making it a more environmentally friendly option.
So a bit of a safety net for the environment. But the study does say we need more research on the environmental safety of this new ZNO at C formulation, right?
Yeah, absolutely. I mean, this study was a great first step. They showed some really promising results in the lab, but more research is definitely needed to really assess how ZNO at sea behaves in different environmental conditions and what its long-term effects might be on various organisms.
Right, because what happens in a lab setting isn't always exactly how things play out in the real world.
Exactly.
Okay, I think we've covered a lot of ground here. For our listeners who might be tuning in while applying their sunscreen, what are the key takeaways from this deep dive?
So the big picture is this. Scientists have created this new compound, ZNO at CH, by combining zinc oxide with chitosan. And in laboratory tests, it's shown some really promising results compared to plain zinc oxide.
Right, like it seems to offer better UV protection, it's more stable across different pH levels, it's less likely to produce those harmful reactive oxygen species on our skin, and it appears to be less toxic to our cells.
Exactly. And all of this points to the possibility of developing sunscreens that are not only more effective at protecting our skin, but are also safer for us and potentially gentler on the environment.
And it's exciting because this new ZNO at C might allow us to use less zinc oxide overall to achieve the same level of protection, which could have benefits for both our wallets and the planet.
Right, right.
Of course, it's important to remember that this is just one study and more research is always needed. The researchers themselves point out that they need to do more testing, like testing the ZNO at sea in higher concentrations, refining the sunscreen formulations, and doing those in-depth environmental safety assessments we talked about.
Yeah, that's all super important.
But I think what's really cool is that this study gives us a peek into the future of sunscreen.
I agree.
It shows that scientists are constantly innovating, looking for ways to make sun protection better and safer for everyone and everything.
Yeah, and it also highlights the importance of thinking beyond just the SPF number when you're choosing a sunscreen.
Exactly. Think about the ingredients, what they are, how they work, and what their potential impact might be.
Right. Become an informed consumer.
Yes. And maybe this deep dive will even inspire some of you to do a little research of your own. Look into some of these new ingredients and see what scientists are up to. It's a fascinating world out there. It's where science, personal health, and environmental responsibility all come together.
And maybe it'll even get you thinking about the bigger picture. Like, as we keep looking for the best ways to protect ourselves from the sun, how can we make sure we're doing it in a way that also protects our planet? And what role will these kinds of innovative materials play in finding that balance? Pretty interesting stuff to ponder.